just as a funding disclosure, this work is funded by the National Science Foundation primarily, and also Calder. It's actually one of a handful of studies that we have funded by NSF to think about how resources and experiences at a high school level kind of affect the pipeline into STEM and engineering degrees. So this is actually not, hadn't been kind of a core line of inquiry for me historically, but it's been a fun thing to think about with this host of collaborators. So just with some quick motivation, for those of you involved in the space, calls to enhance the extent and the diversity of the US STEM workforce is very common, right? So we can think about this because, well, one, STEM workers historically have higher wages than workers in other fields, and this demand for STEM is expected to grow. There's also sort of a competitiveness rationale with this as well, in that there's a number of reports that have been published that suggest that, well, if we don't have a kind of a STEM literate workforce in the US, then we're going to fall behind other peer countries in competitiveness. And then a major focus on this is about diversity of the engineering and STEM workforce, and partly you can think of a lot of reasons why that's important. Loss of productivity, because we're not taking advantage of kind of the full amount of the workforce, and also just equity concerns as well. So there's a widely advocated policy solutions to kind of increase the STEM pipeline, and that's to increase math and science course taking at a high school level. Okay, so for a long time, the first thought was, well, we want to have more STEM workers, so what we need to do is enhance STEM outcomes in college. Okay, there are still a lot of programs that try to look at persistence and recruitment in college, but what we start to believe now is that if we wait until somebody gets to college, that's kind of too late in the pipeline to really move the needle on this very much. And so now what we're talking about a lot is try to increase interest earlier in life, and one of the main spaces that we're trying to do that is in high school. Okay, and kind of a thing that's going to be talked a lot about in this policy arena is math and science coursework. I'm going to mention there's kind of three ways that kind of more math and science coursework can manifest itself from a policy perspective. One is state or district-wide mandatory math and science course requirements. So this is saying instead of needing 2 math classes to graduate from high school in the state of Ohio, you need 3. This could be a district, it could be a state. Another one is what we call STEM-focused schools. Okay, so these are kind of high schools that are specifically for STEM instruction, and they have maybe labs and all kinds of other instructional activities. And then a third one, which is we're going to just call expanded course access, and that's what we're going to look at in this paper. I'll revisit this at the end to talk about why I actually think that expanded course access is intuitively appealing from a policy perspective. But if we think about this kind of policy goal of more math and science courses, then there's actually kind of 3 arenas that we could think about, or 3 solutions that we could think about in encouraging this. All right, so just some kind of quotes to try to convince you that this is an important thing. The top one is the Obama administration. They had a STEM for All campaign. This is from 2016. They say, for high school students, access to core and advanced STEM coursework is an essential part of preparing to enter the workforce equipped with the relevant skills for a broad range of jobs and to successfully pursue STEM degrees and courses in college. Okay, so this kind of quote kind of reflects exactly what we're trying to think about, right? That we were saying, well, we need to provide more access to math and science courses in high school. It'll lead kind of eventually to this expanded STEM workforce. But what I'll kind of show you in a little bit, this has not really been rigorously empirically tested, so we're trying to enter the space in there. I pulled this one off of an Ohio website for this occasion. It's the Ohio STEM Learning Network. STEM education is a key strategy for Ohio's economic success, for stimulating economic development in our state and creating economic opportunity for citizens. A STEM literate workforce will attract investment in jobs, and good jobs and economic opportunity will attract and retain world-class talent. Okay, so even here locally, there's been a lot of emphasis on it, again, just to try to convince you that this is something that people are really talking about in this space. All right, so the research question we're going to ask in this is, are policies that increase access to STEM STEM courses in high school, do they help address STEM expansion and diversity goals, right? So we're basically going to look at 2 intermediate outcomes, and that's going to be STEM initial interest in college, and we're going to look at that by looking at majors. initial major upon entry into college, and STEM degree attainment at four-year colleges as well. Okay, so we have these kind of two intermediary outcomes, and then we're going to look at kind of different flavors of this. We're going to look at course access, kind of in a preferred way, which I'll explain to you, but also some variations of this, and also for different student subgroups as well. We're going to be looking at the state of Missouri. Partly this is just because it was a convenient sample we have access to Missouri state administrative data, and I'll describe this in much more detail later. But we're going to look at about 15 cohorts of every public high school student who attended a public four-year college from about 15 years. It's about 140,000 students from about 500 high schools. And the methods we're going to use are going to be, it's actually not going to be that fancy of a paper, relatively straightforward application of a fixed effects model. Okay? And this is actually to address some kind of endogeneity concerns that had been well articulated in some papers about 20 years ago, but the data just didn't exist to actually examine this. And so what we're going to do is just kind of carefully walk through different types of potential bias in this relationship. We're going to try to convince you that we've ruled out most of the major ones. Okay? And then I'll show you this. We have an extension with an instrumental variable models, which kind of is more akin to what had been done in the past. We have better data for this, but we use this actually to contextualize our findings rather as an identification strategy. Okay? So let's go to the preview of results. They're sort of depressing. Okay? And so, we were talking at dinner last night. I like to estimate these, like precisely estimated null effects for these popular policies that we don't know that much about. And that's pretty much what we're doing here. All right? So we see that changes in STEM course access actually does not lead to any kind of observable changes in STEM enrollment or degree attainment. Now, I'll show you some of the results later. Our results are precisely estimated enough that we think we can rule out effects of one standard deviation change in course access. We can rule out effects greater than about 3 to 5% for our outcomes. So we think that that's pretty precisely estimated. And so we're gonna say that we are kind of confidently finding no effect of these policies. And a key reason for this is that when we look at kind of the pass-through from course access, so more courses become available, and the actual course-taking behavior, we see that pass-through to actually be relatively small. Okay? This might be a little surprising at first, but actually once we get into some of the mechanisms in which we think that this may, that the pass-through may be actually higher, we can see that there's a lot of barriers for that, and a lot of barriers actually for the least privileged students in these schools, and I'll get into all of that later. Yeah, Laura.
Do you think at all about students who might be choosing to do a two-year associate's degree and maybe get to like a medical, technical field?
Yeah, so that's part of the broader project. For just sort of a clean transition matrix here, we're looking at just into the four-year sector. Certainly, one of the pathways that this could work is to, it could increase access to the two-year system, and then that could transition on later. We're not going to be able to look at that here. And what I would say is that from a policy perspective, kind of views on this are all over the map. I think that most of us who study this kind of space think that the community college to four-year college pathway is a good one. I would say that's not universally true for a lot of policymakers as well. So I think that this certainly has a limitation in that way. Can't really speak to whether or not it affects that margin. But I'll also say that this question about the entry directly into four-year college is policy relevant.
So can I just
Sure.
follow up? Does that also capture individuals who got some credit from community college in your sample, or are they eliminated? So it's first time, 4-year only.
So that's right. So it's going to be first time, full-time students, right? So we're also going to kind of exclude people who took substantial time, which we mean more than 1 year between high school and four-year college, or who go part-time. Now, part of the reason for the kind of not having a huge gap time is we're trying to look at kind of the proximate effects of the high school curriculum on colleges. So whether we put in a 2-year, if people go through the 2-year sector or take time off, then the link between kind of the high school and the college becomes a little tougher to make because we don't know if it's, well, maybe it was something at their community college or maybe something in their labor market experience that kind of led to that interest as well. So that's certainly a limitation of what we're looking at.
So may I just ask one more follow-up
Sure. Yep.
about the sample? So does it also exclude individuals who had prior credits in college while in high school?
It does not. So
it includes those, but it doesn't include credits at community college after you graduate.
Right, so basically we look at any college activity after graduation, and if it's not at a public four-year institution in Missouri, then they're excluded from our sample. But if somebody had like a concurrent program or something else as part of their high school experience, then they could be included. And I'll talk a little bit more about some of the kind of implications of our data selection and some of the tests we do to try to eliminate some bias associated with it as well. All right, so, and then we're going to find little to no effect heterogeneity by race and gender. One of the kind of main policy initiatives or policy goals is to really kind of increase the number of women and underrepresented minorities into some of these fields. We actually don't see any results along these lines. We look across kind of schools based on their minority composition. We also look at individuals as well based on their race and gender that's identified in our data. We actually find, if anything, some negative kind of effects of the expanded course access to women and minority students. And what this suggests, so I'll talk about this later, is that actually when you open up courses in high schools, kind of the most privileged students are actually the most likely to take advantage of it, which again is kind of not what the policy goal would suggest, but is actually kind of intuitive when you start.
So you're saying this is like a negative peer effect because you're selecting out the stronger students?
I don't know if it's a peer effect story as much as just think about a story like this. So one of the things that we know is that minority students are tracked to a slower math track on high school on average than our, let's say, white students, right? So let's say, a common way that people will expand course access, they'll say, okay, now we're going to offer Algebra 3 or something like that in high school, right? And so if you have students who have been tracked to go slower on their pathway, then opening up in a more advanced class is actually not going to allow that minority student to take that.
Yeah, I was trying to explain the negative effect. So I'm like, so if you open up this other track and the high quality students or high achieving students go to take advantage of these courses and they're leaving the regular track courses, then maybe you've got a different concentration of students.
Oh yeah, and so maybe I should have been a little more careful with my language. So it's not a negative for them overall, but it's relative to the kind of white male students. And so that's, I should clarify that. Yeah. All right, so the roadmap of the talk, I'm just going to provide you a brief background. I'm going to go through the research design, data and context findings, and then we'll have some time hopefully to talk about implications for policy. Please do ask questions throughout. I'm happy to answer throughout, and that's sort of what I'm a little bit more comfortable with as well. And so if you're sitting on your hands, please don't. All right, so just some background. This is actually a space in which there's been a lot of literature, but few that have asked this question directly, and few that have asked, I think, what is the most policy relevant question, which is about course access. So, I could have written a whole page with citations about kind of examinations into the STEM pipeline. People have been looking at this, again, at a college level, to high school level, kind of, in elementary school at early stages. And there's also kind of a large literature about how high school curriculum affects educational and earnings outcomes as well. Some of this is focused on STEM, some of it is not. But there's kind of, if we look at the nexus of this, there's a pretty strong belief that high school experiences play a role in STEM field interest and preparation for college STEM coursework, right? And if we look at some of the studies that think about course taking in general, a common theme is that high school math and science courses positively predict STEM course interest, right? Now, we're going to see this in our data as well, right? But there's sort of an obvious selection concern here, right? That people who are going to be either more interested or better at math and science in high school are also more likely to be more interested and better at math and science in college, right? And so we have kind of a handful of studies that suggest, hey, if we take more math and science in high school, people are more likely to go in STEM. And so it kind of led to all these policies saying we should have more courses available, right, in high school, without thinking kind of too carefully about the selection issues. All right, just to kind of belabor the point that this is kind of a policy interesting topic. These are all headlines from the past year or so. One's a GAO report. But these are all, again, I could have filled out 20 slides with different headlines here. Basically, a lot of people are saying that, well, high schools are either failing certain students, whether that's women and minority students, or that we need to have more of these courses in high school. So there's kind of a lot of emphasis, if you start to pay attention to this space, thinking about, well, how can we have high school preparation lead to better STEM outcomes in college? And I'll just point this one out here because the conversation has not been universally positive about especially mandating more math and science in high school. And so this is for this is arts instructors saying, well, if you only focus on math and science, then your students are missing out on a lot.
Yeah, a very small thing, Marsh, but if you look at the middle quote on EdSource that Latino and African Americans have less access, this probably should be as take less advantage of more access to math science classes in relation to what you said earlier, right?
They have
less access?
Well, so if you look at what this is referring to is basically a study that shows the number of courses available to students. So this is actually course access, okay? What we're going to say is that we find that they also take less advantage of courses when there is access. But this is just a story, this is not about our paper, but just that when people have looked at this, if you look at schools that are, as the minority composition of the student body increases at many high schools, the number of advanced math and science courses especially declines. All right, so I'm going to walk through the research design first. I'm going to kind of take this step by step because this is kind of what I'm interested in doing. And so hopefully this will kind of articulate the problem that we're trying to address and how we address it. So we want to look at the causal effect, right, of course access or exposure to STEM courses in high school on STEM outcomes in college. And so we're going to start with this question, or kind of a cross-sectional regression, which has been kind of asked a lot in the extant literature on this that has led to some of this policy design. But we're going to think about some outcome, right? We're going to think of like attaining a STEM degree in college, right? We're going to think about that as a function of some level of student level controls. Okay, in our case, we're going to look at academic preparation as measured by high school class rank, ACT scores in math, ACT scores in English. Some level of high school characteristics. In our study, we're going to look at enrollment, underrepresented minority shares, free and reduced price level enrollment, free and reduced price lunch enrollment shares as well. And then a variable of interest here, which we might think of as just courses taken in high school or math and science courses taken in high school. Okay? And so what we want to say, right, we want to interpret this kind of coefficient beta 3 here as the causal effect of, well, conditional on observed individual and high school courses, high school characteristics, what is the effect of an additional course taken in high school on getting a STEM degree? Okay, this is actually what a lot of people have done in the extant literature, right? But we're going to have kind of two well-identified endogeneity threats to this, right? So the first one, which I mentioned before, is that course taking in high school is likely endogenous to college entrance, right? So as I mentioned before, right, better math and science or more interested in it, more likely to take more courses, okay? The other source of endogeneity we're going to have to deal with is that course exposure is also likely endogenous, right? So we like to think about course exposure in this case as like a menu of courses. Right? And so if you're a high school student, you probably have a menu of courses available to you, at least in some degree. And students sort to high schools. Right? And so we're going to have kind of these two endogeneity threats, both which could be related to our outcome and our key variable of interest. And so even though this is what is used often to kind of justify this policy emphasis on high school math and science courses, we know that it's got a lot of problems. So to address the first threat, what we're going to do is we're going to substitute courses taken for courses available. Okay, so now we're going to call this CA. And so what we're going to gain from this is we're not going to have selection into courses, right? So this is going to be basically the menu available to each of these students, right? But not their actual courses taken, okay? Now, a key part of this is that we're going to change kind of the focal or the interpretation of this focal parameter. So now, our delta 3 there is going to be not the effect of taking courses on STEM outcomes, but actual exposure to STEM. Now, we can think of this if you want as moving from like a treatment on the treated to an intent to treat effect, if you want to think of it that way. I also think that this is the most policy relevant way to think about course exposure as well, right? Because if you're a policymaker, right, you can either mandate that a student takes more classes, and I'll talk more about, there's a lot of negative consequences we think associated with that, or you can encourage either districts or states, whether that's through funding or other ways, to offer more courses, right? So we're kind of changing our focal parameter from a treatment on the treated to an intent to treat effect, but we also think this moves this into a more policy relevant measure. Yeah.
It's probably also less correlated with X if you do it that way.
That's right. Another advantage. Thank you. And so there's kind of two kind of groups of the literature. I kind of glossed over this a little bit when talking about the background, but some economists did some studies kind of asking this question somewhat similarly. The last one was, I guess, 15 years ago, but they basically stopped here. Okay, and largely this was because they were using data that didn't permit them to go any further, using kind of national survey data that was low cell at any individual high school. But this is how we're going to kind of take care of the individual selection into course taking. And then when we're thinking about the endogeneity of high school course menus, right, we're going to then add high school and year fixed effects. And this is, again, just because we have this long data panel, we're able to do this. And so we're going to identify the effect of course menus or course exposure on within high school variation over time. Okay? So transparently, one of the costs of doing this is we're going to restrict our identifying variation to just within high school variation. Okay? Again, because we have such a large panel that we can do this, and I'll show you later, we argue that we still have kind of enough statistical power to estimate precisely estimated results. But what we're not going to be able to do is kind of look at sorting across high schools, right? So I'll talk about this at the end, but our results are not going to be informative for things like STEM high schools, right? Because that's really a sorting to high school issue. And what we're talking about is if a high school increases their courses year to year, what effect does that have on students' choices? Okay? Now we still have one primary identification thread, and that's because we're using a long panel, even though it provides us the statistical benefit, we actually have this other threat that things could change over time drastically enough where kind of a high school fixed effect actually kind of doesn't control for everything we think of. Kind of I think an example that we try to use to explain this is think about a gentrifying neighborhood, right? Over 15 years, a neighborhood could change so drastically that the student body changes, the teachers change, the resources change, everything. And so a high school fixed effect is really just doing the average effect over that. It doesn't well capture something that is changing rapidly over time. We're going to do some tests on this later. If we have time, I'll show them to you. Basically, we just estimate the same model in kind of shorter subpanels, and you wouldn't think there's this drastic change. We find exactly the same results. Okay? And so what we think is we've kind of addressed sort of the two main threats to internal validity as part of this. And there is one remaining, but we do some kind of supplementary tests to try to. Yeah.
So how are you thinking about the courses offered? Like what is it like a supplier side shift that's causing that to change?
Yeah, let me kind of address this when I get to the data, and we can talk about courses offered. Okay, but it's a good question. So are there any questions about sort of the empirical approach that we're going to take here? Again, a pretty straightforward approach to this, but we think we're kind of addressing the main sources of bias inherent in asking this question.
Yes. Just to clarify, when you're talking about students sorting into high schools, you're talking about like just where their parents can afford to live, or is that anything other than house?
Yeah, so it could be, your parents move to a different neighborhood because the schools are better there, and that could be the schools are better because there's a lower teacher to student ratio. It could be that there's some other benefits associated with it. Or some students will either, go to still a public, but like a charter school, right? And so like in the Ohio context, this is less common in Missouri, but in the Ohio context, if there's like a STEM high school in your area, you may not move like your physical home, but you may apply to try to get to a magnet school or something like that. Okay. All right, and so then the other thing we're going to do is just this instrumental variables extension. So if we wanted to look at kind of the treatment on the treated effects, what we could do is then estimate as a first stage the courses taken, right, as a function of the course exposure, right, and then use that predicted courses taken based on variation in course exposure, and look at that relationship with STEM outcomes. Okay? Two reasons we're not going to rely on this too heavily. One is kind of with an IB, there's a stronger assumption related to what we call the exclusion restriction. I actually think we can satisfy this decently well, but we're not even going to just kind of get into that at all. And that's partially because when we estimate the first stage of this, just to give you a preview, we see that this relationship between course access and course taking, even though it satisfies what we might think of as a relevance condition within an IB approach, it's statistically strong, it's substantively pretty small. Okay? And so what we're seeing is that, yes, when there's more courses available, it does lead to students taking more classes, but on average, it's so small that it's actually not going to show up very much if we think about this in the second stage. Okay? And so we actually use this then to think about why course access does not have an effect, right? If we thought that course access did have this large effect on STEM degree attainment, we would expect not just a statistically strong first stage, but also a substantively strong first stage. But we just don't have, we only basically satisfy one of those conditions. Okay? All right, so let me get into the data and context here, and we can talk about some of these issues that came up as well. All right, so the context is the Missouri Public University system. There's 13 four-year public universities in the state of Missouri. They're plotted here. The size of the circle is weighted by enrollment. And so basically this is University of Missouri-Columbia where I used to teach. It's by far the largest institution in the state. But about 60% of STEM degrees are either by, are granted either by Missouri-Columbia or this institution here, which is the Missouri Science and Technology, which is a small STEM-focused college. What I don't have on here, but as part of kind of other projects related to this grant, is that if we looked at, especially if we're thinking about a diversity margin, where minority residents live in the state of Missouri, it's almost exclusively on the ends. And this is St. Louis over here, Kansas City over here. So we have these maps that we've done, which we basically take all the minority residents counted in census counts and kind of look at the shares of the distribution. It's basically all here and all there, whereas all of this, or most of the STEM instruction is happening at these two institutions here. So one of the other projects we have looks at, well, does this physical distance actually matter as well? There are a couple universities in St. Louis, the bigger one being University of Missouri St. Louis, and one in Kansas City, University of Missouri Kansas City. But both of those have less than 10% of their degrees in the STEM fields as well. So just kind of one of the contexts here being that we have geographic mismatch between where the colleges are that offer STEM degrees and where a lot of the minority students actually come from.
But could that just be supply and demand as well? So if the kids aren't demanding it in there, they're not going to supply it in those areas? Because if there was more kids demanding it, then you think they might increase the offerings.
Yeah, so it's not as simple as that. In that there's a coordinating board in Missouri that's very strong.
Okay.
I can say off the record between all of us here and on the camera, off the record, when like UMKC or UMSL or this is actually one of the fastest growing institutions right here, it's Missouri State University. When they have wanted to expand into programs, basically Mizzou and Missouri S&T fight against this pretty hard, right? And they're so powerful in the state that they've been effective in restricting that. Now, certainly there's probably a demand issue as well as that, but there's actually a supply constraint as well.
So it's not just fewer degrees awarded, it's actually fewer degree granting programs. In those.
Yes, that's a good way to think.
I thought you were saying there were just fewer degrees and thinking.
Oh, no, yes. Yes, so that like the programmatic options is not evenly distributed across the state here. And actually this is part of the other.
To get a new program, you have to go through a convoluted process.
Yes, that's right. And so if we look at engineering specifically, and there's reasons for this, like engineering programs are really costly, then actually it's 90% of the engineering degrees are at just these two institutions. So, and actually in this other project, we create a bunch of maps and we show that this is pretty true in a lot of states as well, because often it's the flagship institution and maybe a technical institution that are historically were opened up as land grant institutions in the middle of nowhere they're often removed from sort of urban areas, which, at least historically have where we've had a lot of the minority residents.
In terms of other things that get kids excited about STEM fields, I assume those happen more in urban areas, like science centers.
Yeah, so that's interesting in that, like, one of the hot things right now is, like, science centers or visits to museums, natural history museums, science museums, and you're exactly right. I mean, I'm pretty sure Columbia had like a small one, but if you want to go, I mean, the one in St. Louis is fantastic, and so there is like some work trying to be done actually in St. Louis, thinking about, so a student goes to a field trip to a museum, other things, does this lead to interest? And my read on the evidence is that this is generally positive. But then if you think about it as like a barrier, right, and then the student has to travel more than 100 miles to go actually pursue that interest. And so I do think that there is kind of promise there for things that would be available in urban areas, but then there's kind of other barriers associated with it. Yeah.
The other point I would make about is that career technical education, which is quite prominent in rural areas, is a very good provider of STEM coursework and content at an early age. And so there's a lot of unexplored connections between doing Future Farmers of America or something like that in a small town, and then matriculating in an applied STEM field. And I think that's why not including the 2-year stuff is particularly problematic.
Okay.
You're going to miss a lot of that connectivity that's happening.
Yeah, so the doc student I talked about, Felix there, he's looking at specifically kind of rural student pathways into engineering fields specifically. I'm pretty sure he doesn't find kind of a strong pathway from the community college system into the, at least like in Missouri, these universities as well going into engineering. But I think it's a good point to.
But you also don't have Illinois and Kansas too, so you're missing a lot of the potential neighboring states.
Yeah, certainly there can be out-migration out of the state. What you might think of is from like a policy perspective, if you're a state policymaker, then you don't necessarily want your students to go to Illinois or Kansas. There's also a financial consideration associated with that with in-state, out-of-state tuition. There's actually been some kind of movement for like Illinois and Kansas to offer Missouri students in-state tuition and vice versa. So some of that would be lessened in that. But if we kind of, this is looking within the state. So actually there are closer universities in Illinois for the St. Louis resident than in Missouri, but it does come with, again, some other barriers associated. All right, so the data that we're going to look at here is administrative data from the Department of Higher Education in Missouri, data that's maintained at the state, and it has records for all the institutions, but we're going to restrict it, at least in this study, for the 13 four-year public institutions. 14 cohorts, about 15 years, over about 140,000 students. So students are going to declare a major upon entry. Now, what I want to say is that the major declared in our data is not actually the same thing as formally declaring in with the institution, right? So they're basically asked, Stephanie, what are you planning on studying, right? And she can say, hairdressing or engineering, and it's like costless to her, right? But we think that, even though it's measured with error, it's a pretty good indication of their interest. And then we're going to look at STEM degree attainment, which is going to be a degree attainment within 6 years at any of the institutions within this 4-year system, okay? We do the same thing. We look at 7 years, 8 years out. It doesn't really matter in that way as well, so we're just going to use the 6 years. We use zip codes to classify majors following traditional designations. And the Department of Higher Education data is going to have counts of the number of STEM courses completed in high school, class rank, ACT scores, and also demographic information as well. We're going to merge this with high school curricular data from the Department of Elementary and Secondary Education in the state of Missouri. We have 498 public high schools in our data over this time period. And we're going to what we're going to do is aggregate the high school data to create a course menu. Okay? So what we're trying to look at here is how many math and science courses did that student have available over their high school career? Okay? We're going to define this as grades 10 to 12 in this paper, just because some high schools in Missouri are 10 to 12, some are 9 to 12. So we're going to kind of define this as grades 10 to 12 at each high school, and then we're going to merge that on based on the year the student graduated. So we'd be able to say Stephanie graduated in 1996, and so therefore during her 3 years at 10 grades 10 through 12, this was the number of math and science courses available. Okay? What we're going to do is use as our kind of primary measure of course access the 3-year average of the number of STEM courses offered per year per 100 students. Okay? Now, we can think about this in a couple different ways. Our primary measure that I'm going to show you is just kind of the total in this. We also look at kind of divisions by class type and level, so science versus math, regular versus advanced. You know, the grad students actually went through every single course number and said this is an advanced class or not. And then we do some extensions where we look at course sections versus topics. And so kind of the example in this is like, one way to expand course access is to say, I already have 2 sections of biology, I'm going to add a 3rd section, right? And so that's just to try to like address pent-up demand. Or you could say, I already have biology, I'm going to add physics, right? And so under our main measure, every section that gets added is kind of equally. We also do this other measure called topic availability, which is basically if a new topic is added. And then we also unadjust, or we use a measure that's unadjusted for student enrollment as well, just thinking there might be some kind of like absolute effect that's important as well. I'll just say that kind of all of the results, regardless of how we think about this, kind of are all directionally the same. Yeah.
So, quick question. Do you have any sense of what else is changing as course availability is changing? I assume there's like some budget constraints. If you have more STEM courses, you have fewer other stuff, or if you have more STEM courses, they're smaller. Like what the other kind of the bundle treatment is.
Yeah, so it's a good question. We haven't looked at this. And so I guess we could look, for example, we have measures of other classes, English, arts, other things. So we could look to see if it's like it's changing behavior by high schools in a way that would crowd out arts or something like that. It's a good suggestion. We have not done that in this case. Rob, did you have anything?
Are there remedial classes that get counted as regular?
The short answer is it could, right? We basically looked at course titles and numbers to do this. What the Department of Higher Education does is when they say Rob has taken a math course, is it's basically a course that qualifies for the Missouri Coordinating Board's standards, and that's like pre-algebra would not count for that, okay? We tried to kind of parse that out as well. It's really hard kind of based on looking at course titles to do that, so what we did instead was just like group that in with regular. We tried to do some sensitivities, like looking at what we might call, quote unquote remedial classes, and it's just really noisy to do, and we just think it's measured with a lot of error.
Not to veto the course in some ways, but to a certain extent, this is why leaving out the post-secondary courses enrolled while you're in high school is a problem, because in the last 5 or 6 years nationally, those courses have become a very strong percentage of the top students' enrollments.
Oh, we're not leaving those out.
So you said you don't consider enrollments while they're in high school and college. You said that.
No, I was saying that wouldn't exclude them from the same. I thought you were asking if somebody takes high school or college courses while in high school, if that would exclude them from the sample, and it does not exclude them from the sample.
So are those recorded then in their curriculum data?
It wouldn't be in the curriculum. It would be in the courses taken, but not the curriculum. Right, but again, if we think about the policy margin associated with this, right, the high school, that's not a policy margin. The high school. What they could do is encourage students to take classes at that, but that's not like a resource necessarily.
Well, in many states, I don't know the specific policy environment in Missouri. It would be interesting to know, but in many other states it would be. It's something that's a common pool of resources that are shared among school districts. I don't know the Missouri context as well as I should be making these comments, and I apologize.
Well, so the way that I would think about it is that's like an investment by the post-secondary system to make their courses available, right? Because these are college courses.
Paid for often by the K-12 system or by by subsidies. So it's not necessarily, capacity is simply like Rob opening a new course here, it's not whether we as a school district elect to enroll students. So I would just consider it, and I would look at the policy in Missouri.
Okay, yeah, we can take a look at that. What I would say is that I don't know if there's kind of within this research design a way to capture that in the data. I would have to think more thoughtfully about that, but I think that might be something that's just not observable in the data. All right, so let's talk about some consideration. Actually, before we do that, let's go back to Lauren's comment. Sorry, what was your question again?
I mean, it's kind of the same question of like what's causing the increase in the local courses? Is it that there is increased demand, or there's some kind of external shock on the supply side that allows them to open up?
Yeah, so there was sort of an external shock after our sample was finished, in which Missouri raised basically the recommended number of courses that students had to take, and also it was both the required courses to graduate and the recommended number of courses they had to take. That led to students kind of proactively, even though that was after our time period, like the high schools knew that this was coming, and so they proactively started to offer more courses. We would capture that in our data. If it was just a demand story where there was like pent-up demand, and we're not seeing that because we're not seeing a lot of that pass through from course access, of course.
Do you see a lot of changing courses over time? I mean, is there a lot of heterogeneity? This is all based on identifying within school changes.
Yeah, I mean, there's so I mean, we like 20% of our variation in course offering is within high school.
schools.
Yeah.
Okay. So
And it goes down as well as up.
What's that?
So it goes down as well as up when it comes to STEM courses, or is there like, it's almost always going
Oh,
down?
that's a good.
Well, so when we look at it kind of standardized by the number of students, it can go up and down, right? Because if you, and like if you think about like course offerings, like it's kind of a step function, right? And so if you have one marginal extra student, you don't need to offer a new course if there's pent-up demand. But once you hit 20 or 40, and it kind of depends on the high school, it can as well. We're not seeing a formal step function that we can like plot out, but like in talking to folks, this is kind of typically what we would see. So it might be that kind of demand is increasing because just like more students are at that school. A lot of, again, like in the Missouri context, there was just a lot of thought like, hey, this is what we need to do is just offer more courses, and so high schools compete for students as well. I mean, it was just sort of like, oh, now we're going to add computer science courses, or now we're going to add a more advanced class as well. And so it was common in the context.
So the size of the school though is changing. The denominator is changing too every year. And so some of your heterogeneity is being driven by enrollments that are changing. And so the number of course offerings may not change, but the enrollments are changing. That's positive. Is that right?
That could happen, but then when we use kind of the unadjusted measure, then
it's okay.
Then we would not have that
And
issue.
you have the unadjusted measure and it holds.
Yes, that's right.
Okay.
So it's
Okay.
sensitivities. We
Okay.
unadjust by course enrollment. In that case, we're rarely going to see sort of a decline. You actually, like in some rural areas and other things in which they've had a huge population decline, you might see a decline. But this is one of the reasons we kind of adjust and unadjust as well. All right, so considerations with the sample restrictions. Public high school students, again, this is kind of not looking at private students. I think it's the most policy relevant group. We can include private high schools and it doesn't change the results. And students who matriculate into Missouri public four-year institution. And so some of you may be thinking, well, what if this changes who goes to college or where they go, right? And what we'd be worried about is, what if all of a sudden all these Missouri students start going to Purdue or MIT or Georgia Tech or all these places? This is a function of our data availability. What I will say is we do basically a battery of tests to look at, well, does the ACT scores change? Does the college going rates change? Does the four-year college going rate change? Does the two-year college going rate change? Does the average ACT in our sample change class rank? We basically don't see a relationship between year-to-year changes in courses and kind of matriculation into the system. Okay, and so we're going to not be that worried by this fact, though we can't, we have no formal way of for sure saying this isn't happening. Okay, so just for the sake of time, I'm going to kind of just go quickly through some of the results and summary statistics. So when we look at college STEM outcomes, this is all going to be based on our data. Male students certainly more likely to declare a major in STEM upon entry and actually graduate with a STEM degree. When we look by race, we do see some differences. Asian students more likely to be interested in STEM and get a degree, but Hispanic, white, and black students actually somewhat close in their STEM interest. But then when we see kind of what we see is sort of Hispanic students who initially major in STEM are less likely to get a STEM degree than our white students. The same thing is true for black students as well. Math and science courses taken in high school, we actually see males and female students a very similar rate. This is kind of documented in other literature, which may be surprising to you given that, well, male students are so much more likely to be interested in STEM in college and get a STEM degree. And then again, we see sort of an Asian advantage in math and science courses taken in high school, but the rest of the racial ethnic groups are somewhat similar. Math and science courses available in high school, don't see a male-female difference really. There is a little bit difference by race and ethnicity. Largely this is going to be driven in some ways by enrollment size as well, but they're all actually, the point estimates are very similar to each other as well. All right, so let me kind of speed through and get to the results. In this first row here, what I'm going to show you is basically kind of what people have estimated in the literature. So this is courses taken, and then the outcome's either going to be major or degree attainment. What we see here is a statistically significant relationship, and what I would say is that this magnitude is also large. All right, so we can translate these into effect sizes. What I'm going to kind of characterize things as a 1 standard deviation change in courses taken. If we translate this, that's about a 15 to 20% increase, right, for each course taken. So it's basically this finding that people have talked about. Take more courses, more likely to either major or get a degree in STEM. And then what we do on this bottom row is then try to address some of these endogeneity issues. And so then what we can think about is kind of the first two columns for each outcome, so columns 1 and 2 and 4 and 5, being accounting for maybe selection of courses themselves, but not the endogeneity of course menus. When we go to kind of our preferred model, which is in blue here, what we find are basically results which are close to 0 and then precisely estimated. And again, if we kind of look at 1 standard deviation in courses courses available, which in our data is about 3.5 courses, 1 standard deviation change in this is about 3% of the mean in initial major, the upper bound, sorry, if we look at the upper bound of this, and about 5% in degree attainment. So we're saying kind of the upper bound of our 95% confidence interval for a 1 standard deviation change, we can rule out effects larger than about 3 to 5%, which we think is precisely.
So, so you think it's 5 percentage points in
5% of the mean. 5% of the average, right? So we can say with confidence that a 1 standard deviation, so if a high school offers 3.5 more courses per year, that we can say with confidence that we are unlikely to see an effect on the probability somebody gets a STEM degree of over 5%.
5 percentage points? So like
No, 5%.
5% total.
So we would think about like, you take this 0.0003, multiply by 3.5, and then divide it by the average, which is about 12% of students.
Okay, so yeah, I guess that's.
So it's more like, I don't know how to do that math in my head, but 0.1 of a percentage point.
Okay.
I'm just going to speed through some of this just for the sake of time. We split out math courses into this regular advanced. We don't really see any differences there. When we look at topic availability or this unadjusted measure, this is all kind of in the appendix of the paper. We see similar results to our main results. Here's the first stage of our IB. Effectively, we're going to estimate courses taken as a function of courses available. We can see that they're strongly statistically significant. But again, if we try to think about whether this is practically significant at all, we spent a lot of time trying to think about like what would we expect if there was pent-up demand. We talk about this in the paper, but we would expect if there's pent-up demand for this coefficient to be like 0.2 to 0.6 if we thought that there was really pent-up demand for this. And with our estimates using high school fixed effect, we're at 0.02. In this estimate without the high school fixed effect, we're at 0.04. This is also subject to sort of the endogeneity bias for cross-school sorting. But this is all to say that basically we would expect this to be much higher if the story was there was all this demand for courses that once you offer them, a lot more students will take them. Yeah.
Have you thought about trying to do something with the timing? Because it seems like if you're already in grade 11 and they're adding the courses and you didn't have the course in grade 9, then you're kind of out of luck. So maybe like looking at the first year and what courses are available then and seeing if that.
Yeah, so we've tried to do this, and it just gets pretty complicated to do it.
Sure.
We actually think this is one of the stories as to why we don't see this, right? And that, so a lot of places will have science requirements, right? So you'll take your 3 science classes, and then maybe they'll add some other class, but you say, you know what, I've already taken the science that I needed, right? Or maybe they'll offer another class, but I need to take 3 more classes before I get to that class, and I can't take it. So it's hard for us, given the curricular data that we have, to do that here, but we think that this is part of the reason, right? Like, a lot of students, even if a course is added, just don't have the opportunity really to take those courses, right? And we actually think this is part of the kind of privileged student story. We actually think that the kind of women and underrepresented minority students are less likely.
Did you just test legs? Could you just leg course availability so that you'd be looking at course availability from several years back and see the impact or test whether the legs mattered?
We could. Yeah, could do that. That's a good suggestion. All right. I'm going to just kind of go through this. This is, we did some tests for dynamic bias. 2 dimensions of effect heterogeneity regarding diversity. I don't want to kind of make too strong claims on this, but we look at kind of high schools by the enrollment share of students, of underrepresented minority students, which in this case we're going to look at as Black or Hispanic. And then within high schools, between individual students by race and gender. Again, for the sake of time, I'm just going to speed through this. We don't see sort of a bigger effect for students or schools that have higher shares of minority students, and partly this question was driven by some of the policy push on this. This is where we see some kind of relative to the white male students, the marginal kind of effect of an extra course for female and underrepresented minority students is negative. We see a negative point estimate. We can argue really that the point estimates are pretty small, so I don't know how much we should really draw upon this. But if we believe these to be true, what that would suggest is that white males, when there's an extra course available, are more likely to take advantage of that than are female students or underrepresented minority students.
And you think about on the first stage, so is there like, if you head up and down in certain types of districts that had like really low availability, so did you try the first stage in these different subgroups? You might have a strong instrument for like certain urban areas or rural areas.
We did not. I guess like we'd be imposing some sort of assumption of what it meant to have like low availability, though I think we could make some relatively non-controversial assumptions on that. Yeah, I mean, that's
it doesn't matter if the root reduced more, I guess doesn't work.
It's a good idea. We have not done that, but it's a good idea. So, summary of findings. What we find is expanded access to STEM coursework. It's unlikely to expand the scope of post-secondary STEM education. A lot of limitations which we've talked about, both because it's specific to Missouri and because we're only looking at one of the 3 potential policy initiatives related to this. So let's talk about what this means for policy. So one of at the beginning I talked about how one of the ways that people can, or states could introduce, or states or districts could introduce more math and science courses is to have these STEM-focused schools. The literature, as I've read it, says that there are positive outcomes for students who go to STEM schools, but once you start to control for potential selection into these schools, kind of that goes away, right? So we don't actually have good evidence that this is kind of causally affecting STEM outcomes, and it's also somewhat controversial in kind of where these are located, who gets in, how people enroll, and who pays for it. Another set of policy options for this is course taking mandates. As I mentioned before, this is kind of states or districts saying everybody has to take more math or more science or both to be able to graduate. The evidence is mixed. We do see some kind of higher academic outcomes in some cases, but a common theme is that it actually has a lot of negative consequences as well. Right? So if you raise the standards for high school graduation, we see in almost all of these contexts that high school graduation then declines as well. Right? And so even though this had been very popular, some of these negative outcomes associated, especially with students that these policies are supposed to help, people have started to back away from this policy as well. So all else equal, this voluntary course exposure policies that we're thinking about in this paper, we think this is intuitively appealing for the policymaker, and this is actually where a lot of people have been, kind of the margin people have been pushing on. But I mentioned at the beginning that you can interpret our results as being somewhat depressing because we find that kind of when courses are opened up, the actual pass-through to course taking is not very strong. And so kind of the takeaway for this is that we think that part of this means that we need to do some other things. There's been some more promising interventions to increase STEM interest that are not just, hey, let's offer another math class, but whether that's some sort of immersive experiences. People are thinking a lot about what it means to have a math and science class, so there's kind of some cool stuff going on with robotics and other things in schools as well. But we think that that's a more promising margin on which to push to be able to increase more STEM interest. All right, so I'm going to try to conclude. I got 1 minute left with a conclude poem loosely resembling a limerick. For those of you who are kind of like really attuned to this, don't count the number of syllables. So high school STEM boosts prosperity, said pundits with temerity, but only course access does not yield STEM progress and might even work against parity. Right? So if you don't remember anything else, maybe you'll remember the poem as the takeaway. Yeah, of course. What do you think I do in my free time? All right, so as I mentioned, this is kind of part of a broader project. We're trying to ask some questions related to this idea with a team of graduate students, I think. So please do get in touch if you have any questions about it.